There's a fairy tale you probably know. A young girl wanders into a cottage in the woods and finds 3 bowls of porridge. One is too hot, one is too cold, one is just right. It's a simple story about finding the perfect balance, about the narrow band between extremes where comfort lives. And tonight, as you settle in, as your breathing slows, and the day's concerns begin to fade, we're going to explore how this children's tale has become one of the most important concepts in our search for life beyond Earth. Because out there, orbiting stars scattered across the galaxy are worlds of every imaginable description. Planets baked by their suns until their surfaces glow like coals. Planets so distant from their stars that any atmosphere has long since frozen solid and fallen as snow. And somewhere in between, perhaps, are worlds like ours. Planets where the temperature is neither too hot nor too cold, where water can exist as a liquid, pooling in oceans and flowing in rivers, where life, as we understand it, might have a chance. We call these places habitable zones, the regions around stars where conditions might be just right. But as we'll discover tonight, being in this zone is only the beginning of the story. They involve atmospheres and magnetic fields, planetary size and geological vigor, the character of the star itself, and even the passage of time. The cosmic real estate market, it turns out, is far more selective than we first imagined. So let me take you on a journey. We'll start with the simple elegance of the habitable zone concept, that band of orbital distances where liquid water could exist. Then we'll peel back the layers, exploring the intricate web of conditions that must align for a world to sustain life. We'll visit planets around distant stars, examine the peculiar challenges of red dwarf systems, and contemplate the moving target of habitability as stars age and brighten. Along the way, we'll marvel at Earth's remarkable fortune. We'll wonder at the knife-edge balance that keeps us comfortable. And we'll ask the question that haunts all astronomers who search the night sky. Are we common or rare? Is the galaxy filled with Goldilocks planets, or are we extraordinarily lucky to be here at all? The answers, as we'll see, remain uncertain. But the questions themselves reveal something profound about our place in the universe. So close your eyes if you wish. Let your mind wander among the stars, and let's begin at the beginning with a simple question of distance and energy. Imagine standing on a world with no name, no atmosphere, just bare rock beneath your feet. Above you, a star shines. Not too different from our sun, perhaps. A steady yellow disk in an alien sky. That star is pouring energy into space in all directions. Photons stream outward in an endless flood, carrying with them the heat and light generated in the star's core. Most of this energy shoots past you into the infinite dark, never touching anything. But some of it, a tiny fraction, strikes the surface beneath your feet. Every square meter of this world absorbs roughly a kilowatt of stellar energy, perhaps a bit more, perhaps a bit less. The exact amount depends on one crucial factor: distance. Move closer to the star, and that energy flux increases dramatically. The intensity of starlight follows what physicists call the inverse square law. Double your distance, and you receive 1/4 the energy. Halve your distance, and you receive 4 times as much. It's a simple geometric consequence of light spreading through 3-dimensional space, but its implications are profound. This is where the habitable zone begins, not with biology or chemistry or complex planetary science, but with this fundamental relationship between distance and energy, because that energy determines temperature. And temperature determines whether water can exist as a liquid. In our solar system, Earth orbits the Sun at an average distance of about 150 million kilometers. Astronomers call this distance 1 astronomical unit, or 1 AU. At this distance, Earth receives approximately 1,000 360 watts of energy per square meter of surface area facing the Sunday. That's the solar constant, the baseline energy that drives our weather, our seasons, our climate, and it's just right. Not too much, not too little. Enough to keep our oceans liquid, our atmosphere flowing, our planet alive with the sound of wind and rain and crashing waves. Move inward, though, and the story changes. Venus orbits at 0.72 AU, about 28% closer to the Sun than we are. That seemingly modest difference means Venus receives nearly twice the solar energy we do. The result is a world where lead would melt on the surface, where the atmospheric pressure could crush a submarine, where any ocean that ever existed long ago boiled away into space. Move outward, and you encounter the opposite extreme. Mars orbits at 1.52 AU, about 50% farther from the Sun than Earth. It receives less than half our solar energy. On Mars, the average temperature hovers around -60 degrees Celsius. Any liquid water exposed to the thin Martian atmosphere would quickly freeze or, if the pressure is too low, sublimate directly into vapor without ever becoming liquid at all. These are our neighbors. One too close, one too far. And between them, in a band that includes Earth's orbit, lies the Sun's habitable zone. Scientists define this zone precisely. The inner boundary represents the distance where a planet would experience what's called a runaway greenhouse effect. Here, stellar heating would vaporize any surface water. Water vapor is itself a potent greenhouse gas, trapping more heat, causing more water to evaporate, in a positive feedback loop that ends with the planet's oceans completely lost to space. This is likely what happened to Venus, though the details remain debated. The outer boundary marks the distance where even a thick carbon dioxide atmosphere couldn't generate enough greenhouse warming to keep water liquid anywhere on the surface. Beyond this line, planets freeze into permanent ice balls unless some other source of heat intervenes. For our Sun, the current habitable zone extends from about 0.9 AU to perhaps 1.5 AU. That's the generous, optimistic estimate. More conservative calculations, accounting for various atmospheric complications, might narrow that range to 0.95 to 1.4 AU. Either way, Earth sits comfortably within it. Mars perches near the outer edge, technically inside by some estimates, but clearly struggling with the cold. Venus lies well beyond the inner boundary, baked by excessive solar flux. This is the foundation. Distance determines energy received. Energy received determines temperature. Temperature determines whether water can remain liquid. And liquid water is the medium in which life, as we understand it. But here's where the story deepens, where the simple elegance of this distance-based definition begins to reveal its limitations. Because temperature alone doesn't determine whether water remains liquid. The presence and character of a planet's atmosphere matters enormously. The reflectivity of its surface affects how much energy gets absorbed versus bounced back into space. The planet's rotation rate influences how that energy distributes globally. And beneath all of this lies the question of where the water came from in the first place and whether the planet can hold on to it. Being in the habitable zone we're about to discover is necessary but far from sufficient. The first stroke of luck in a series of cosmic coincidences that must all align for a world to remain genuinely habitable over the billions of years required for complex life to emerge. So let's dive deeper. Let's examine what happens when a planet finds itself at just the right distance from its star, and then ask, what else must go right? A planet at the right distance from its star has potential. But potential means nothing without an atmosphere. Consider the Moon. It orbits Earth, which means it sits squarely within the Sun's habitable zone at the same 1 AU distance we enjoy. Yet the Moon is spectacularly inhospitable. Its day side reaches temperatures above 100 degrees Celsius, hot enough to boil water. Its night side plunges below negative 150 degrees Celsius, cold enough to freeze carbon dioxide solid. There's no liquid water, no rivers, no lakes, no possibility of surface life as we know it. The reason is obvious. The moon has essentially no atmosphere. With a mass too small to generate sufficient gravity and a surface that bakes in direct sunlight for 2 weeks at a time during its long day, the moon lost any gases it might once have possessed. What little atmosphere exists now consists of stray atoms knocked off the surface by solar wind particles, a wisp so tenuous it barely qualifies as atmosphere at all. Without air to distribute heat, to trap and retain energy, to shield the surface from the harshness of space, the moon demonstrates that location alone guarantees nothing. An atmosphere does several crucial things for a planet in the habitable zone. First, it acts as a blanket, trapping heat that would otherwise radiate away into space. This is the greenhouse effect, and despite its negative connotations in discussions of climate change, it's absolutely essential for habitability. Without any greenhouse warming, Earth's average temperature would hover around negative 18 degrees Celsius, well below the freezing point of water. Our oceans would ice over, life would be impossible, or at least vastly different. The greenhouse effect works through absorption and re-emission of infrared radiation. Visible light from the sun passes relatively easily through the atmosphere and warms the surface. The surface then radiates this energy back outward as infrared heat. But certain gases in the atmosphere, particularly carbon dioxide, water vapor, and methane, absorb infrared radiation efficiently. They trap this heat, warming the lower atmosphere and the surface below. It's a delicate thermodynamic dance, one that can maintain a planet at comfortable temperatures even at distances where raw solar flux alone would leave the surface frozen. Earth's atmosphere provides about 33 degrees Celsius of greenhouse warming. That's the difference between our actual average temperature of 15 degrees Celsius and the negative 18 degrees we'd experience without atmospheric trapping of heat. Mars, despite having an atmosphere composed of 95% carbon dioxide, gets only about 5 degrees of greenhouse warming because its atmosphere is so thin. The total atmospheric pressure on Mars is less than 1% of Earth's. There simply isn't enough gas to trap sufficient heat. Venus, on the other hand, demonstrates the opposite extreme. Its atmosphere is nearly 100 times thicker than Earth's, and also composed primarily of carbon dioxide. The greenhouse effect on Venus has gone completely out of control, raising surface temperatures to nearly 470 degrees Celsius. This is hotter than Mercury, despite Mercury being much closer to the Sunday. The runaway greenhouse effect made Venus what it is today, a hellscape of crushing pressure and searing heat, where the very rocks glow dull red in the dense twilight that passes for daylight on the surface. But atmospheric pressure and composition represent only part of the equation. An atmosphere must also be stable over geologic time. It must resist being stripped away by stellar wind, a concern we'll return to shortly. And its composition must be regulated somehow, kept in a range that maintains moderate temperatures rather than spinning off into extremes. On Earth, this regulation happens through the carbonate-silicate cycle, one of the planet's most important feedback mechanisms. When Earth's atmosphere contains too much carbon dioxide and temperatures rise, increased rainfall and weathering of rocks draws CO2 out of the air and locks it into carbonate minerals. These carbonates eventually get subducted into the mantle through plate tectonics, then released again through volcanic outgassing, completing the cycle. If temperatures drop too low, weathering slows, volcanic outgassing continues, CO2 builds up again, and greenhouse warming brings temperatures back up. It's an elegant thermostat, operating on timescales of hundreds of thousands to millions of years. And it requires several things to work: a geologically active planet with volcanism, liquid water to enable weathering, and some form of plate tectonics, or at least mantle overturn, to recycle the carbonate rocks. Not every planet will have all these ingredients. Mars certainly doesn't anymore. Once upon a time, Mars likely had a thicker atmosphere, perhaps thick enough to allow liquid water to flow on its surface. The ancient riverbeds and lake beds we see in satellite imagery testify to a wetter past. But Mars is small, with only about 11% of Earth's mass and 38% of our surface gravity. That weak gravity couldn't hold onto the atmosphere as well as Earth does, and when Mars's interior cooled and its magnetic field died, a process we'll examine in detail shortly, the loss accelerated dramatically. Today, Mars's atmosphere is a ghost of its former self, too thin to prevent water from freezing or sublimating, too thin to provide meaningful greenhouse warming despite being nearly pure CO2. The reflectivity of a planet's surface also plays a subtle but important role, working in concert with atmospheric effects. This reflectivity, called albedo, determines what fraction of incoming sunlight gets absorbed versus bounced back into space. Fresh snow has a high albedo, reflecting up to 90% of sunlight. Dark ocean water has a low albedo, absorbing most of the light that hits it. Rock and soil fall somewhere in between, typically reflecting 10 to 40% of incoming light. Albedo creates feedback loops of its own. If a planet starts to cool and ice forms near its equator, that ice reflects more sunlight, reducing the amount of energy absorbed, causing further cooling and more ice formation. This can lead to snowball Earth scenarios, where the entire planet freezes over, which geological evidence suggests happened at least twice in Earth's history. Breaking out of such a frozen state requires enough volcanic CO2 to build up in the atmosphere over millions of years, eventually warming the planet enough to start melting the ice. Once melting begins, the darker surface of ocean or rock absorbs more sunlight, accelerating the warming in a positive feedback that reverses the snowball state. For planets around red dwarf stars, which emit much of their light in the infrared rather than visible wavelengths, albedo effects work differently. Ice and snow reflect visible light well but absorb infrared more readily. This might actually extend the habitable zone around red dwarfs somewhat, allowing planets to maintain warmer temperatures at greater distances than we'd expect based on visible light alone. The story of atmospheres, then, is the story of regulation and balance. Too thick, and you get a Venus. Too thin, and you get a Mars. Just right, and you get an Earth. But maintaining just right over billions of years requires more than fortunate initial conditions. It requires ongoing geological activity, stable surface conditions, and protection from the harsh environment of space. Which brings us to our next requirement, one that's invisible but absolutely crucial. A planet needs a shield. It needs a magnetic field. Deep beneath your feet, if you're on Earth, a dynamo churns. In the planet's outer core, about 3,000 kilometers below the surface, liquid iron flows in vast convective currents. The temperatures there exceed 4,000 degrees Celsius, hot enough to keep iron molten. The pressures are immense, measured in millions of atmospheres, and in this hellish environment, a magnetic field is born. The physics of planetary dynamos is complex, involving the interplay of rotation, convection, and electrical conductivity. But the basic principle is understood. Moving molten iron, itself a good electrical conductor, generates electrical currents. These currents create magnetic fields. The planet's rotation organizes these fields into a coherent structure, typically a dipole with north and south magnetic poles, like a bar magnet buried at Earth's center. This magnetic field extends far beyond the solid Earth, reaching out into space for tens of thousands of kilometers. On the sunward side, it extends about 10 Earth radii before being compressed by the solar wind. On the night side, It stretches out into a long magnetotail extending hundreds of Earth radii. The shape reminds scientists of a teardrop or of water flowing around a rock in a stream. And this invisible structure, this bubble of magnetic field lines surrounding our planet, is one of the most important things protecting us from space. The sun, you see, doesn't just emit light and heat. It also throws off a continuous stream of charged particles, mostly electrons and protons, traveling at speeds between 300 and 800 kilometers per second. This is the solar wind, and it carries with it about 1 million tons of matter every second, spiraling outward through the solar system and beyond. When these charged particles encounter Earth's magnetic field, something remarkable happens. The field deflects them. Charged particles moving through a magnetic field experience a force perpendicular to their motion, causing their paths to curve. Most of the solar wind particles are diverted around Earth's magnetosphere, flowing past like water around a boulder. Some particles do get trapped in the magnetosphere, spiraling along field lines and accumulating in the Van Allen radiation belts, toroidal zones of intense particle radiation surrounding the planet. And some particles find their way into the polar regions, where field lines dip down toward Earth's surface, creating the auroras as they collide with atmospheric atoms. But crucially, the magnetosphere prevents the solar wind from directly interacting with Earth's upper atmosphere. This matters enormously because without that protection, the solar wind would gradually strip away our atmosphere over hundreds of millions to billions of years. We know this because we can see it happening to Mars. Mars once had a magnetic field. Evidence for this comes from magnetized rocks in Mars's ancient crust. These rocks preserve the signature of a global magnetic field that existed over 4 billion years ago when the rocks formed and cooled, locking in the magnetization. But Mars is small, and small planets cool faster than large ones. The ratio of volume to surface area matters here. A smaller planet has more surface area relative to its interior volume, allowing heat to escape more efficiently. By about 4.1 billion years ago, Mars's core had cooled enough that the dynamo shut down. What happened next was inevitable. Without a magnetosphere, the solar wind began interacting directly with Mars's upper atmosphere. Charged particles collided with atmospheric atoms and molecules, transferring energy. Some of this energy went into heating the upper atmosphere. Some went into ionizing atoms, stripping electrons away and creating charged ions. And crucially, some went into accelerating atmospheric particles to escape velocity, allowing them to flee into space. The Mars Atmosphere and Volatile Evolution mission, which orbited Mars from 2014 until 2022, directly measured this atmospheric loss. Today, Mars loses about 100 grams of atmospheric material per second to space, the majority of it oxygen ions and carbon dioxide molecules that have been broken apart and accelerated by solar wind interactions. This might not sound like much, but over 4 billion years, it adds up to the loss of a substantial atmosphere. Mars's thin, cold atmosphere today is the end result of this long, slow hemorrhaging of gases into space. Earth, protected by its magnetic field, loses atmosphere too, but at a much slower rate. During a 2008 planetary alignment that allowed direct comparison, scientists used ESA's cluster spacecraft at Earth and Mars Express at Mars to observe both planets being hit by the same stream of solar wind. The results were striking. Mars lost oxygen at 10 times the rate Earth did. The difference in atmospheric loss rates over billions of years is staggering. Venus presents a puzzle in this framework. Venus has essentially no magnetic field, just a weak field induced in its ionosphere by solar wind interactions. Yet, Venus has retained an incredibly thick atmosphere. How? The answer seems to be that Venus's atmosphere is so thick that its sheer mass provides protection. The ionosphere of Venus extends far into space, acting as an obstacle to the solar wind without needing a true magnetosphere. The solar wind does remove some of Venus's atmosphere, but the rate is slow enough that the massive atmosphere survives. Venus also lacks the large moon that Earth has, which means no tidal forces to potentially enhance atmospheric loss. An early Venus may have been protected by different solar wind conditions when the Sun was younger. But Venus's situation is precarious. If Venus had started with Earth's atmospheric mass instead of nearly 100 times more, it might have lost its atmosphere entirely by now. The protection from atmospheric thickness only works if you have enough atmosphere to start with. The magnetic field requirement adds another constraint to our growing list of habitability criteria. A planet needs sufficient mass to generate strong gravity to hold an atmosphere, but it also needs to maintain geological activity long enough to keep a dynamo running in its core. Small planets like Mars cool quickly and lose their magnetic fields early in their history. Large planets might maintain fields longer, though we're still learning about how planetary mass, composition, and thermal evolution interact to determine magnetic field longevity. And here's a subtle but crucial point. Generating a magnetic field requires not just a molten core, but also planetary rotation. The Coriolis effect, arising from the planet's spin, helps organize the convective currents in the core into coherent patterns that generate a stable dipole field. A planet that rotates very slowly, perhaps because it's become tidally locked to its star, might struggle to maintain a strong magnetic field, even if its core remains molten. This becomes a serious concern for planets in the habitable zones of red dwarf stars, as we'll explore in detail later. The magnetic shield, then, is not a luxury but a necessity for long-term habitability. Without it, even a planet at the perfect orbital distance with an initially perfect atmosphere will gradually be sterilized by its star's own wind. But a planet's habitability depends on more than just keeping the atmosphere it has. It depends on regulating that atmosphere's composition over geological time. And that requires something else. A living, breathing, geologically active world. Earth churns. Beneath its thin, solid crust, heat flows upward from the interior, driving convection in the mantle, moving continents, building mountains, triggering earthquakes and volcanic eruptions. This geological vigor is not merely dramatic scenery. It's essential for maintaining habitability over the immense timescales required for complex life to evolve. The connection between geological activity and atmospheric regulation runs deep. Remember the carbonate-silicate cycle we discussed earlier? That cycle depends on volcanic outgassing to return carbon dioxide to the atmosphere after it's been locked away in rocks. Without volcanism, without tectonic recycling of those carbonate rocks into the mantle, where they decompose and release CO2, the cycle breaks. Carbon gets permanently sequestered. The atmosphere gradually loses its greenhouse gases. Temperatures drop. The planet freezes. This appears to be part of what doomed Mars. Mars shows evidence of extensive volcanism in its past. Olympus Mons, the largest volcano in the solar system, towers 21 kilometers above the surrounding plains. The Tharsis volcanic plateau could have been built only by billions of years of sustained volcanic activity. But Mars hasn't seen a major volcanic eruption in perhaps tens of millions of years, possibly much longer. Without sufficient internal heat, mantle convection weakened. Volcanism sputtered and died. And with it died any chance of maintaining a stable, thick atmosphere through the carbonate-silicate cycle. Plate tectonics, Earth's particular form of geological activity, offers special advantages for atmospheric regulation. At subduction zones, where one tectonic plate slides beneath another, oceanic crust gets dragged down into the mantle. That oceanic crust contains carbonate minerals formed from atmospheric CO2 that dissolved in seawater and reacted with the crust. By subducting these carbonates, plate tectonics continuously remove CO2 from the surface environment. At mid-ocean ridges and volcanic arcs, magma rising from the mantle releases gases, including that same CO2, back into the atmosphere and oceans. The cycle completes. We're still not certain why Earth has plate tectonics while Venus, similar in size and composition, does not. Venus appears to resurface itself through episodic global volcanic events rather than continuous, steady recycling through plate tectonics. This might actually be less efficient for regulating atmospheric CO2, though the details remain debated. What's clear is that Earth's particular geological style has proven remarkably effective at maintaining moderate temperatures for over 4 billion years. The connection between planetary size and geological longevity follows straightforward physics. Larger planets have more mass, which means more gravitational self-compression, which generates more heat. They also have more volume relative to their surface area, meaning heat escapes more slowly. A planet twice Earth's mass might remain geologically active for tens of billions of years. A planet half Earth's mass, like Mars, goes cold within a few billion years. Recent modeling suggests that planets in the range of 0.5 to 1 Earth masses will become geologically dead within about 5 to 7 billion years. After that point, they must rely solely on their star's luminosity to maintain habitable temperatures, with no help from volcanic outgassing to regulate atmospheric CO2. For comparison, Earth is about 4.5 billion years old and remains vigorously active. We likely have billions of years of geological activity ahead of us. But a planet with only 0.6 Earth masses would already be geologically dead by now if it formed when Earth did. Super-Earths. Planets with masses between 1 and 10 times Earth's might actually have advantages for long-term habitability. Their greater mass means stronger gravity, which helps retain atmospheres even without magnetic fields. Their larger size means they stay geologically active longer, maintaining volcanism and atmospheric regulation for extended periods. The challenge with super-Earths is that we don't yet know how their geology actually works. Do they have plate tectonics? Do they resurface episodically, like Venus? Or do they settle into some other regime entirely? These are questions we'll need to answer through observations of actual super-Earths in the coming decades. Tidal heating provides an alternative energy source for geological activity, one that doesn't depend on the planet's initial heat budget. When a planet orbits close to its star or has a slightly eccentric orbit that varies its distance, tidal forces from the star can knead the planet's interior, generating heat through friction. Jupiter's moon Io experiences such intense tidal heating from its proximity to Jupiter that it's the most volcanically active body in the solar system, despite being smaller than Earth's moon. For exoplanets in the habitable zones of red dwarf stars, which orbit very close to their hosts, tidal heating might provide significant additional energy. This could help smaller planets maintain geological activity even after their internal heat has largely dissipated. However, tidal heating typically also leads to tidal locking. The picture emerging is of habitability as a dynamic equilibrium rather than a static state. A planet at the right distance, with the right atmosphere and the right magnetic field, might still lose habitability over time if its interior cools and goes geologically dead. Conversely, a planet that starts out too cold might become habitable later as its star brightens or as greenhouse gases accumulate through volcanic outgassing. Habitability, we're realizing, is not just about where a planet is, but about what it's made of, how big it is, and how its interior evolution proceeds over billions of years. The requirements keep stacking up: right distance, right atmosphere, right magnetic field, right size, right geological activity, and we haven't even addressed the character of the star itself. Because different stars have different habitable zones, and not all habitable zones are created equal. The type of star matters enormously, and some types of stars, despite being the most common in the galaxy, might be the most challenging places for life to gain a foothold. Our Sun is, in many ways, unremarkable. It's a G-type main sequence star, classified as G2V in the spectral sequence that astronomers use. Its surface temperature sits at about 5,800 Kelvin. Its mass is, by definition, 1 solar mass. It generates energy through the fusion of hydrogen into helium in its core, and has been doing so steadily for about 4.6 billion years. It will continue for another 5 billion years or so, before swelling into a red giant and eventually shedding its outer layers to become a white dwarf. But the Sun represents only one point on a spectrum of stellar possibilities. Stars come in a range of masses, temperatures, luminosities, and lifetimes. And each type of star imposes different conditions on any planets that might orbit in its habitable zone. Let's start at the hot end of the spectrum. F-type stars are more massive than the Sun, typically 1 to 1.4 solar masses, with surface temperatures ranging from 6,000 to 7,500 Kelvin. They shine brighter than the Sun, which means their habitable zones lie farther out. An F-type star might have a habitable zone extending from 1.5 to 2.5 AU, well outside Earth's orbit if that star were transplanted to replace our Sunday. The advantage of F-type stars is that their habitable zones are wider, offering more real estate where liquid water could potentially exist. The disadvantage is that F-type stars live shorter lives than G-type stars. An early F-type star might burn through its hydrogen fuel in only 2 to 3 billion years before evolving off the main sequence. This matters because life on Earth took about 3.5 billion years just to develop multicellular organisms, and another billion years to develop intelligent life. If complex life generally requires several billion years to evolve, F-type stars might not provide enough time, especially for their brighter members. G-type stars, like our Sun, occupy a sweet spot. They live for about 10 billion years on the main sequence, providing ample time for life to evolve. Their habitable zones are neither too narrow nor too wide, making it reasonably likely that a planet might form or migrate into the right orbital distance. And they're bright enough that observing and characterizing planets in their habitable zones, while challenging, is within reach of our current and near-future technology. Then we come to K-type stars, sometimes called orange dwarfs. These stars have masses between 0.6 and 0.9 solar masses, and surface temperatures between 3,900 and 5,200 Kelvin. They're cooler and dimmer than the Sun, so their habitable zones lie closer in, typically between 0.4 and 0.9 AU. Many astrobiologists consider K-type stars the true Goldilocks stars for habitability. They live even longer than G-type stars, with main sequence lifetimes extending from 15 billion years up to 50 billion years or more for the coolest K-dwarfs. That's plenty of time for life to evolve, with billions of years to spare. Their habitable zones, while closer to the star than our Sun's, are still wide enough to be accessible. And K-type stars are more common than G-type stars, making up perhaps 12 to 15% of all stars compared to 7 to 8% for G-types. K-type stars also tend to be less magnetically active than smaller stars, producing fewer dangerous stellar flares once they settle into their main sequence lives. They emit less ultraviolet radiation than hotter stars, which reduces the risk of atmospheric erosion. If you were designing a star from scratch to maximize the probability of habitability, you might well choose a K-type star. Long-lived, stable, common, with a generous, habitable zone. But K-type stars represent only a small fraction of the galactic population. The real majority are the M-type stars, the red dwarfs. And this is where things get complicated. M-type stars, also called M-dwarfs, or simply red dwarfs, have masses ranging from about 0.08 solar masses, just barely massive enough to sustain hydrogen fusion, up to 0.6 solar masses. Their surface temperatures fall between 2,400 and 3,900 Kelvin, making them glow with a dull red light. They're dim, with luminosities ranging from 0.01 down to 0.0001 times the sun's output for the smallest ones. And they're everywhere. Current estimates suggest that 70 to 85% of all stars in the Milky Way are M-dwarfs. If you picked a star at random from our galaxy, there's about a 3 in 4 chance it would be a red dwarf. With perhaps 250 billion stars in the Milky Way, that means somewhere around 180 to 210 billion red dwarfs, each one a potential host for planets. Moreover, red dwarfs live virtually forever by stellar standards. A red dwarf with 0.1 solar masses will burn hydrogen for trillions of years. The universe is currently only 13.8 billion years old, which means every red dwarf that has ever formed is still on the main sequence, still shining steadily. No red dwarf has ever died of old age. None will, for countless eons to come. With such longevity and such abundance, red dwarfs should be prime targets in the search for habitable worlds. If complex life needs billions of years to evolve, red dwarfs offer time beyond measure. If habitable planets are rare, red dwarfs offer sheer numbers to compensate. By simple statistics, even if only 1% of red dwarfs host habitable planets, that's still billions of potentially life-bearing worlds. But there's a problem. Actually, there are several problems, and they all stem from the same basic fact. To be in the habitable zone of a dim star, a planet must orbit very, very close. A red dwarf with 0.3 solar masses and 1%. The sun's luminosity has its habitable zone centered around 0.1 AU. That's closer to the star than Mercury is to our Sunday. An even smaller red dwarf might have its habitable zone at 0.05 AU or less, where a year lasts only a few Earth days and the star looms enormous in the sky. This proximity creates challenges we haven't encountered with larger stars. Challenges related to tidal forces, stellar flares, magnetic field generation, and the character of the stellar radiation itself. Understanding these challenges, and whether life might overcome them, represents one of the most important questions in modern astrobiology. So let's turn our attention now to these small red stars and ask, can the most common stars in the galaxy host habitable worlds? Or does their very nature doom any planet in their habitable zones to sterility? Imagine standing on a world that circles a red dwarf. The star in your sky is not the familiar yellow disk of our sun, but something stranger. It's huge, perhaps 3 times the diameter our sun appears from Earth, because you're orbiting so close. But it's dim, glowing with a deep red hue like cooling embers. The light it casts seems wan, almost twilight even at noon. And there's something else. As you stand there, watching this crimson sun, you realize something unsettling. It never moves. The star hangs fixed at one point in the sky, neither rising nor setting. Day here is eternal. And somewhere on the other side of this world, hidden from your view, the night is equally eternal. This planet is tidally locked to its star. Tidal locking occurs when gravitational forces synchronize a planet's rotation period with its orbital period, so that the same hemisphere perpetually faces the star. It's the same phenomenon that keeps one face of the moon forever toward Earth. And for planets orbiting close to their stars, as habitable zone planets around red dwarfs must, tidal locking is nearly inevitable. The timescale for tidal locking depends on several factors: the distance to the star, the masses involved, and the planet's size and structure. But for Earth-sized planets orbiting at 0.1 AU or less, tidal locking happens quickly, typically within a few million years. Given that red dwarfs live for trillions of years, any planet in the habitable zone has almost certainly been locked in this synchronous rotation for nearly its entire existence. What does this mean for habitability? The traditional worry was atmospheric collapse. If one side of the planet faces eternal daylight while the other faces eternal night, the day side would heat up while the night side would cool down. Eventually, it was thought, the night side would become so cold that its atmosphere would freeze out, snowing down to the surface as solid nitrogen or carbon dioxide or whatever gases dominated. This condensation would lower atmospheric pressure everywhere, causing more atmosphere to migrate toward the night side and freeze out in a runaway process that would end with all the atmosphere frozen on the night side and the day side a bare, airless desert. However, more sophisticated three-dimensional climate models developed over the past 2 decades have shown that this catastrophic outcome is unlikely if the planet has a sufficiently thick atmosphere. Atmospheric circulation can distribute heat from the day side to the night side efficiently enough to prevent complete freezing. Even a relatively thin atmosphere, perhaps comparable to Earth's, appears sufficient to avoid collapse. The winds would be fierce and constant, blowing from the hot substellar point toward the cold night side, but the atmosphere would remain gaseous. So, atmospheric collapse might not be the death knell for habitability that was feared, but tidal locking creates other problems. For one, slow rotation likely weakens a planet's magnetic field or eliminates it entirely. Magnetic dynamos require the Coriolis effect from planetary rotation to organize convective flows in the core. A tidally locked planet might rotate once every 10 Earth days, or once every 20 days, or even less frequently depending on its orbital period. This slow rotation substantially weakens the Coriolis effect. Computer simulations suggest that tidally locked terrestrial planets might generate magnetic fields only 10% as strong as Earth's, or perhaps no coherent dipole field at all. Without a strong magnetic field, the planet becomes vulnerable to atmospheric erosion by stellar wind, exactly as we discussed with Mars. This becomes especially problematic around red dwarfs because they tend to be magnetically very active, producing stellar winds and coronal mass ejections that can strip away planetary atmospheres even more aggressively than the solar wind strips Mars. Which brings us to stellar flares, perhaps the most serious challenge facing any planet in a red dwarf's habitable zone. Red dwarfs are violent stars, especially when young. They experience frequent stellar flares, sudden increases in brightness caused by magnetic reconnection events in the star's atmosphere. During a flare, the star's luminosity can increase by factors of 10, 100, or even 10,000 inches the X-ray and ultraviolet portions of the spectrum. These high-energy photons slam into any planet orbiting nearby, potentially breaking apart atmospheric molecules and accelerating atmospheric loss. For planets orbiting very close, as habitable zone planets around red dwarfs must, the intensity of this radiation can be extreme. During a large flare, a planet at 0.1 AU might receive 100,000 times more X-ray and ultraviolet flux than Earth receives from the Sun, even during solar flares. This radiation can erode atmospheres, break apart water molecules with the light hydrogen escaping to space, and shower the surface with harmful, ionizing radiation that would damage or destroy any organic molecules or primitive life forms. Young red dwarfs flare frequently, perhaps several times per day for the first few billion years of their lives. The conventional wisdom has been that planets around red dwarfs would need to survive this flare phase before life could gain a foothold. Once the star ages and calms down after a few billion years, conditions might improve enough for life to emerge and evolve. But observations have complicated this picture. In 1998, astronomers observed a massive flare from Barnard's star, a red dwarf about 10 billion years old, at least twice the age of our Sunday. The flare was so intense that Barnard's star briefly became brighter in X-rays than the quiet Sunday. This suggests that even old red dwarfs can remain magnetically active, never fully settling into the calm stability that would benefit habitability. Moreover, the Transiting Exoplanet Survey satellite mission, which completed an all-sky survey between 2018 and 2020, has revealed that red dwarf flares are even more common than previously thought. A study of 112 bright red dwarfs observed by TESS identified over 2,500 optical flare events, suggesting that flares occur more frequently than models had predicted. And optical flares are almost always accompanied by X-ray flares, meaning the high-energy radiation environment around red dwarfs is even harsher than we realized. Tidal heating adds another layer of complexity. Planets in the habitable zones of red dwarfs often have slightly eccentric orbits rather than perfectly circular ones, especially if there are other planets in the system tugging on them gravitationally. This eccentricity means the planet's distance from the star varies slightly over its orbit. Those variations, combined with the planet's tidally locked rotation, create flexing and stress in the planet's interior, generating heat through tidal friction. In moderate amounts, tidal heating could be beneficial, helping to maintain geological activity on small planets that might otherwise cool and go geologically dead. But excessive tidal heating could make the planet's interior too hot, leading to runaway volcanism and outgassing that thickens the atmosphere beyond habitable limits. Finding the right balance would require specific orbital configurations. And yet, despite all these challenges, the story of red dwarf habitability is not entirely pessimistic. Three-dimensional climate models have shown that tidally locked planets can maintain habitable conditions in certain regions, even if the full globe isn't uniformly habitable. The Terminator Zone, the ring around the planet where eternal sunrise or sunset occurs, might offer mild temperatures and liquid water, even if the rest of the planet is too hot or too cold. Ocean circulation could help distribute heat, creating a band of habitability that wraps around the planet at the day-night boundary. Planets with substantial oceans might fare better than dry planets. Water has high heat capacity, meaning it takes a lot of energy to change its temperature. Oceans can absorb heat from the dayside and slowly release it, moderating temperature extremes. They can also drive strong atmospheric circulation through evaporation and condensation, further distributing heat globally. If a planet could maintain a thick atmosphere and strong magnetic field, perhaps through tidal heating, maintaining geological activity and core convection, it might resist atmospheric erosion even in the face of stellar flares. The magnetic field would deflect stellar wind. The thick atmosphere would absorb flare radiation before it reached the surface. Life might find refuge in oceans or underground, protected from surface radiation. And there's the simple argument from numbers. Even if red dwarf planets face steep odds against habitability, there are so many red dwarfs that even a small percentage hosting habitable worlds would still represent billions of life-bearing planets in our galaxy alone. Evolution is creative. Life on Earth has adapted to extreme environments we once thought uninhabitable. Deep-sea hydrothermal vents, acidic hot springs, radiation-bombarded deserts, the perpetual darkness of caves, and the deep ocean. The question remains open. Recent statistical analyses have suggested odds of about 1,600 to 1 against red dwarfs hosting advanced civilizations comparable to Earth's, based on our limited observations. But this is based on relatively sparse data and many assumptions. We're still in the early stages of characterizing planets around red dwarfs, still building the models and gathering the observations we need to answer this question definitively. What we do know is that we've found many planets orbiting in the habitable zones of red dwarf stars, and some of them are tantalizing targets for further study. So let's turn our attention now to specific worlds, to the actual planets we've discovered orbiting in their stars' Goldilocks zones, and ask, what have we learned? In 2009, NASA launched a spacecraft called Kepler with a simple but ambitious goal: stare at a patch of sky containing about 150,000 stars and watch for the tiny dips in brightness that occur when a planet passes in front of its star. For nearly 4 years, Kepler watched without blinking, measuring the brightness of these stars thousands of times. The mission revolutionized our understanding of planets beyond our solar system. When Kepler was launched, we knew of only a few hundred exoplanets. By the time the mission ended in 2018, after a technical failure forced a change in strategy, Kepler had discovered over 2,600 confirmed planets and identified thousands more candidates awaiting verification. Among Kepler's discoveries were dozens of planets orbiting within their stars' habitable zones. But one statistical pattern emerged that surprised astronomers. The most common type of planet in the galaxy appears to be one we don't have in our solar system: super-Earths and mini-Neptunes, planets with sizes between Earth and Neptune and masses perhaps 2 to 10 times Earth's, dominate the planetary population. These intermediate-sized worlds are everywhere. We just can't easily see them around sun-like stars because their transits create such tiny dips in stellar brightness. Around smaller, dimmer stars, though, the detection becomes much easier. The same planet blocking the light of a red dwarf creates a much deeper transit because the star's disk is smaller. This observational bias means that most of the characterized planets in habitable zones orbit red dwarfs, despite the challenges we just discussed. Consider the TRAPPIST-1 system, perhaps the most famous exoplanetary system discovered in recent years. TRAPPIST-1 is an ultra-cool red dwarf located about 40 light-years from Earth in the constellation Aquarius. With only 8% the mass of our Sun and less than 0.1% of the Sun's luminosity, it's barely massive enough to fuse hydrogen at all. In 2016, astronomers using a small robotic telescope in Chile called TRAPPIST announced the discovery of 3 Earth-sized planets orbiting this dim star. Follow-up observations with NASA's Spitzer Space Telescope revealed something astonishing. There were actually 7 planets, all roughly Earth-sized, all orbiting closer to their star than Mercury orbits our Sunday. The entire TRAPPIST-1 system is incredibly compact. All 7 planets orbit within 0.06 AU of their star, a distance that would fit comfortably inside the orbit of Mercury. From the surface of one of these planets, the other planets would appear in the sky larger than the Moon appears from Earth. You could potentially see clouds and continents on neighboring worlds with the naked eye. 3 of the 7 planets, designated TRAPPIST-1e, F, and G, orbit squarely within the star's habitable zone. Planet E is particularly interesting. It orbits at 0.028 AU, with a period of 6.1 Earth days. Its size is about 92% of Earth's diameter, and its mass is about 69% of Earth's mass, giving it a density similar to Earth's, suggesting a rocky composition. It receives about 66% of the stellar flux Earth receives from the Sun, which with the right atmospheric greenhouse could maintain surface temperatures suitable for liquid water. Computer models of TRAPPIST-1e suggest it might be covered by a global ocean with a climate similar to Earth's. If so, it would be the most Earth-like exoplanet discovered so far in terms of overall habitability prospects. But we don't yet know if it has an atmosphere. This is where the James Webb Space Telescope enters the story. Launched in December 2021 and now operating at a gravitationally stable point beyond the Moon's orbit, JWST has the sensitivity to probe the atmospheres of planets transiting small, dim stars like TRAPPIST-1. In 2023, JWST observed multiple transits of TRAPPIST-1 planets, allowing scientists to search for atmospheric absorption signatures. The results for the innermost planet, TRAPPIST-1b, were discouraging. No evidence for any atmosphere at all. The planet's dayside temperature measures about 500 Kelvin, and the observations matched what would be expected for bare rock with no atmospheric heat redistribution. This makes sense. TRAPPIST-1b orbits far too close to be habitable and has likely been stripped of any atmosphere by stellar radiation over its 8 billion year lifetime. For TRAPPIST-1e, the atmospheric story remains unclear. Initial observations hinted at possible methane in the atmosphere, which would be fascinating because methane could be a biosignature in certain contexts. But the signal was tentative and could also be explained by stellar contamination. What JWST is teaching us is that characterizing the atmospheres of small, rocky planets is extraordinarily difficult, even with the most powerful telescope ever built. The signals are subtle. The stellar contamination is troublesome. Each observation requires many transits to build up sufficient signal-to-noise ratio. It's painstaking work, but it's the work that will ultimately tell us whether planets like those in the TRAPPIST-1 system can maintain atmospheres and, by extension, whether they might be habitable. Another famous habitable zone planet is Proxima Centauri b, orbiting the closest star to our Sun at a distance of just 4.2 light-years. Discovered in 2016 using the radial velocity method, which detects the tiny wobble in a star's motion caused by an orbiting planet's gravity, Proxima Centauri b appears to be roughly Earth mass, perhaps 1.3 times our mass. It orbits Proxima Centauri, a red dwarf, at a distance of 0.05 AU, with an orbital period of 11.2 days. This places Proxima Centauri b squarely in its star's habitable zone, receiving about 65% of the stellar flux Earth gets from the Sunday. With the right atmosphere, it could have surface temperatures suitable for liquid water. But Proxima Centauri is known to be a flare star, erupting with large flares regularly. In 2019, a massive flare increased the star's brightness by a factor of 68 inches, the ultraviolet, over just 10 seconds. If Proxima Centauri b was in the line of fire, it would have received a dose of radiation equivalent to what Earth gets in a decade, compressed into a few minutes. Whether Proxima Centauri b has managed to maintain an atmosphere in the face of such bombardment remains unknown. Unlike TRAPPIST-1 planets, Proxima Centauri b doesn't transit its star from our viewing angle, which means we can't use transit spectroscopy to probe its atmosphere. Future extremely large telescopes on the ground might be able to detect light reflected off the planet and analyze that for atmospheric signatures, but those observations are years away. Around Sun-like stars, the discoveries are more challenging but no less intriguing. Kepler 452b, announced in 2015, orbits a star very similar to our Sun at a distance of 1.05 AU, almost exactly Earth's orbital distance. The planet is about 60% larger than Earth and likely has a mass about 5 times Earth's, making it a super-Earth. It receives only 10% more energy from its star than Earth receives from the Sunday. Kepler 452's star is about 1.5 billion years older than our Sun and slightly brighter. This means Kepler 452b has had longer to develop life if conditions were right, but also that it may be approaching the inner edge of the habitable zone as its star has brightened over time. Models suggest the planet likely has active volcanism and geological activity given its mass, which would help regulate atmospheric CO2. But whether it has oceans, what its atmosphere is like, whether it's more like Earth or more like Venus, these questions remain unanswered. The sheer distance to these planets, typically dozens to hundreds of light years away, makes detailed characterization extremely difficult. We can measure their sizes from transit observations and estimate their masses from gravitational effects, allowing us to calculate density and guess at composition. But determining atmospheric composition, surface temperature, and the presence of water requires much more sensitive observations than we can currently make for most of these worlds, which is why the next generation of space telescopes is so important. NASA's proposed Habitable Worlds Observatory, designed specifically to find and characterize Earth-like planets around Sun-like stars using direct imaging rather than transits, could potentially take spectra of the reflected light from dozens of potentially habitable worlds. Those spectra might reveal water vapor, oxygen, ozone, methane, and other gases that could indicate habitability or even life. But even as we build better telescopes and find more candidates, a troubling realization has emerged. The habitable zone is not a fixed thing. It moves. It evolves over time as the star itself brightens and changes. 4.5 billion years ago, when Earth had just finished forming from the swirling disk of dust and gas around the young sun, our star was different than it is today. It was cooler, dimmer. Its luminosity was only about 70% of its current output. This creates a puzzle that's haunted planetary scientists for decades. With 30% less solar energy warming the early Earth, our planet should have been frozen solid. The oceans, if they existed at all, should have been ice from pole to pole. Life should never have gotten started. And yet we have geological evidence from ancient rocks and sediments, that liquid water existed on Earth's surface as far back as 4.4 billion years ago, almost from the very beginning. This is the faint young sun problem, and it's one of the classic mysteries in Earth science. The most widely accepted solution involves greenhouse gases. If the early Earth had an atmosphere much richer in CO2, water vapor, methane, and possibly ammonia than today, those gases could have trapped enough heat to compensate for the dimmer Sunday. Carbon dioxide levels might have been 100 or even 1,000 times higher than today. Methane, produced by early microbes if life existed that early, or by geochemical processes if it didn't. These gases would have created a thick thermal blanket around the planet, keeping temperatures above freezing despite receiving substantially less sunlight. Recent research has highlighted the importance of collision-induced absorption, a subtle quantum mechanical effect where pairs of molecules like CO2 and H2, pressed close together in a dense atmosphere, can absorb infrared radiation that neither molecule could absorb alone. In a thick early atmosphere rich in hydrogen gas, this effect could have provided significant additional warming, potentially solving the faint young sun problem for both Earth and Mars. Mars presents an even more dramatic version of the puzzle. The geological evidence for liquid water on early Mars is extensive. Valley networks that look like ancient river systems, mineral deposits that form only in the presence of water, sedimentary rocks indicating ancient lakes. Yet early Mars received only about 43% of the solar energy that early Earth received. Because it's farther from the Sunday, how did Mars stay warm enough for liquid water? The answer likely involves an even thicker atmosphere than Earth's, possibly sustained by volcanism and greenhouse gases. But the key word is early. Mars apparently lost that thick atmosphere within its first billion years or so, as we discussed earlier when examining the role of magnetic fields. Mars cooled, its dynamo died, stellar wind stripped away the atmosphere, and the planet transitioned from a potentially habitable world to the frozen desert we see today. The fundamental point is that stars brighten as they age. This is a consequence of how stellar fusion works. As hydrogen fuses into helium in a star's core, the helium accumulates and the core gradually contracts under its own gravity. This contraction heats the core, causing the fusion rate to increase. More fusion means more energy output, so the star's luminosity rises. For a star like our Sun, this increase is gradual but relentless, roughly 1% brighter every 100 million years, or 10% per billion years. This means the habitable zone moves outward over time. When the Sun was young, the inner edge of the habitable zone might have been around 0.8 AU, closer to the Sun than Venus's current orbit. Today, That inner edge lies around 0.95 AU, well inside Earth's orbit. In another billion years, it will be near Earth's orbit. In 3 or 4 billion years, Earth will be inside the inner boundary, receiving too much solar flux to maintain liquid water, even with minimal atmospheric greenhouse effect. Venus may have experienced exactly this fate. Early in the solar system's history, when the sun was dimmer, Venus might have orbited within the habitable zone. It might have had moderate temperatures, liquid water, perhaps even primitive life. But as the sun brightened, Venus slid past the inner edge of the habitable zone. The runaway greenhouse effect began. Water evaporated, trapped heat, caused more water to evaporate, in a feedback loop that ended with Venus's current hellish state. Similarly, Mars may become habitable in the future. As the sun continues to brighten, the outer edge of the habitable zone will move beyond Mars's current orbit. If Mars could somehow regain a thick atmosphere, perhaps through human terraforming efforts or through volcanic outgassing that our current models don't account for, it might become a world where liquid water could exist on the surface. This temporal evolution of habitable zones has led scientists to define a more stringent concept: the continuously habitable zone, or CHZ. This is the region where a planet could maintain liquid water not just at one moment in time, but continuously from the early days of the star's main sequence life all the way to the present. For our Sun, the continuously habitable zone from 4 billion years ago to today extends from about 0.95 to 1.15 AU. That's a narrow band, much narrower than the instantaneous habitable zone at any single epoch. Earth orbits at 1 AU, placing us comfortably within the CHZ. Mars, at 1.52 AU, lies outside the CHZ entirely, never having been within the habitable zone for the full 4 billion years. Venus, at 0.72 AU, may have been in the CHZ for a while early on but exited it billions of years ago. For planets around other stars, the CHZ depends on stellar type and age. More massive, hotter stars brighten faster over their main sequence lifetimes, which means their CHZs are narrower. Less massive, cooler stars brighten more slowly, which could mean wider CHZs, except that these stars' habitable zones are already quite narrow because the stars are so dim. Recent modeling has identified F and G-type stars as optimal for long-term habitability when considering the CHZ. These stars are massive enough to have reasonably wide habitable zones, but not so massive that they evolve too quickly. A late F-type or early G-type star might offer the widest continuously habitable zone of any stellar type, combined with main sequence lifetimes long enough for complex life to evolve. K-type stars, while living even longer, have narrower CHZs because their habitable zones are already constrained by their lower luminosity. And M-type red dwarfs, despite their extreme longevity, have such narrow habitable zones to begin with that their CHZs are quite restrictive, especially when combined with all the other challenges we discussed for red dwarf planets. There's another temporal consideration. Geological activity declines over time as planets cool. This means that even a planet in the CHZ might lose habitability if it becomes geologically dead and can no longer regulate its atmosphere through volcanic outgassing and tectonic recycling. Models suggest that Earth mass planets remain geologically active for about 5 to 7 billion years. Earth is 4.5 billion years old, so we're still in good shape. But a similar planet that formed just 2 billion years earlier than Earth might already be geologically dead today, unable to regulate atmospheric CO2 and potentially no longer habitable despite being in the CHZ. This creates a sort of habitability window in time. Too early, and the planet might not have had time to develop life. Too late, and the planet might be geologically dead. The optimal time for finding life on an Earth-like planet might be between 4 and 6 billion years after the planet's formation, which for stars like our Sun means planets in systems that are between 4 and 6 billion years old. For biosignature detection, this timing matters. Life on Earth took about 2 to 2.5 billion years to develop photosynthesis and begin producing significant amounts of oxygen. Oxygen and ozone in a planet's atmosphere are among the strongest biosignatures we can look for with current and near-future telescopes. But if we're observing a planet younger than 2 billion years, even if it has life, it might not have detectable oxygen yet. Conversely, if we're observing a planet older than 7 billion years around a sun-like star, it might be geologically dead and no longer habitable even if it once hosted thriving biospheres. All of this temporal complexity means that identifying potentially habitable planets is not just about finding planets in the right place, but finding planets of the right age, orbiting stars of the right type and age, with the right geological activity remaining. The Habitable Worlds Observatory mission and other future efforts are beginning to incorporate these temporal considerations into their target selection strategies, using the concept of a CHZ2 metric that calculates the probability that a planet has remained in the CHZ for at least 2 billion years, the approximate time it took Earth's life to become detectable from space. Stars like our Sun, between 4 and 6 billion years old, score highest on this metric. Younger stars haven't given planets enough time for biosignatures to develop. Older stars' planets may have already lost habitability. But as we contemplate these temporal dimensions, we should also acknowledge that our focus on liquid water and traditional habitable zones might be too narrow. Life might find ways to exist in places we haven't even thought to look. Jupiter's moon, Europa, is a world of ice. From space, it appears as a brilliant white ball, its surface a crust of water ice, perhaps 20 or 30 kilometers thick, crisscrossed with dark reddish streaks and complex networks of cracks and ridges. The surface temperature reaches -160 degrees Celsius, cold enough that the ice is as hard as granite. Europa orbits at 5.2 AU from the Sun, far beyond the traditional habitable zone. And yet scientists believe that beneath that ice shell lies a global ocean of liquid water, perhaps 100 kilometers deep, containing more than twice as much water as all of Earth's oceans combined. The heat that keeps this ocean liquid comes not from the Sun but from tidal forces. Europa orbits Jupiter in a slightly eccentric orbit, meaning its distance from the planet varies over its 3.5-day orbital period. Jupiter's enormous gravity kneads Europa's interior as these distances change, generating heat through friction. This tidal heating is sufficient to keep the subsurface ocean liquid despite the frigid conditions at the surface. And where there's liquid water and energy, there might be life. Europa's ocean likely remains in contact with a rocky seafloor, allowing chemical interactions that could provide nutrients for life. Geological activity driven by tidal heating might create hydrothermal vents on the seafloor, similar to the black smoker vents in Earth's deep oceans that host thriving ecosystems, powered not by sunlight, but by chemical energy from the vents themselves. Saturn's small moon Enceladus tells a similar story. Only 500 kilometers in diameter, tiny enough to fit inside Arizona, Enceladus has a subsurface ocean beneath its south polar region. We know this ocean exists because geysers at the South Pole shoot plumes of water vapor and ice particles hundreds of kilometers into space. NASA's Cassini spacecraft flew through these plumes and detected not just water, but also organic molecules, salts, and molecular hydrogen, all of which suggest chemical reactions between water and rock at the base of the ocean. These are the ingredients for habitability. Even Saturn's largest moon, Titan, with its thick nitrogen atmosphere and seas of liquid methane on the surface, might harbor a subsurface water ocean beneath its icy crust. Titan is definitely not habitable on its surface by Earth standards, but beneath the surface, liquid water might exist, kept warm by tidal heating and radiogenic decay. These discoveries have revolutionized our understanding of where life might exist. Subsurface oceans, don't require their host worlds to orbit in any star's habitable zone. They can exist on moons orbiting gas giants or on planets at any orbital distance, sustained by tidal heating or radiogenic decay or both. They might even exist on rogue planets, worlds ejected from their star systems and wandering through interstellar space, kept warm by internal heat alone. Earth itself hosts a vast, deep biosphere, ecosystems living in rocks and sediments kilometers below the surface, far from sunlight, sustained by chemical energy from interactions between water and minerals. These organisms, mostly bacteria and archaea, might represent a significant fraction of Earth's total biomass. They demonstrate that life doesn't necessarily need stellar energy at all. If subsurface oceans can host life, the number of potentially habitable worlds in the galaxy increases dramatically. Every large moon around every gas giant planet becomes a candidate. Every icy dwarf planet beyond the traditional habitable zone becomes a candidate. We might be living in a galaxy where habitable environments vastly outnumber stars. But there's a catch. Subsurface ocean worlds are extremely difficult to detect and characterize. We can't see beneath their ice shells. We can't sample their oceans directly without sending a mission there, drilling through the ice and exploring underwater, which is decades away for places like Europa and even longer for exoplanetary systems. And detecting biosignatures from subsurface life is nearly impossible unless that life affects the surface environment, or, as with Enceladus, unless the ocean contents are conveniently sprayed into space where we can sample them. So, while subsurface oceans expand the theoretical number of habitable environments, they don't much help our near-term search for life beyond Earth. For that, we remain focused on the traditional circumstellar habitable zone, on planets with surface oceans and atmospheres we can observe and characterize remotely. There's another extension of the habitable zone concept worth mentioning: desert worlds. A planet doesn't need to be covered in oceans to be habitable. It might have only limited surface water, concentrated in equatorial regions or in protected valleys, with most of the planet being arid desert. Such a world might avoid the runaway greenhouse fate of Venus because it simply doesn't have enough water to create a thick water vapor atmosphere. The limited water could remain stable in specific locations. Some models suggest that desert worlds might actually have wider habitable zones than ocean worlds. With less water vapor in the atmosphere, there's less greenhouse warming, which means the planet can survive closer to its star without overheating. Conversely, because there's less water to freeze, the planet might remain habitable farther from the star than an ocean world would. Dune. Frank Herbert's fictional desert planet, Arrakis, might not be such an unrealistic scenario after all. Desert worlds with sparse but precious water resources, with life adapted to extreme aridity, might be common outcomes of planetary evolution, especially for worlds that never accreted much water during their formation or that lost substantial water to space early in their history. Binary star systems offer yet another wrinkle in habitability considerations. A planet orbiting two stars, like the fictional Tatooine from Star Wars, receives energy from both stars combined. Depending on the star's masses and the planet's orbital configuration, this could create stable, habitable conditions or highly variable ones. If the planet orbits both stars in a circumbinary orbit, far enough out that the two stars appear as a single, bright, binary system in the sky, the habitable zone would be determined by the combined luminosity of both stars. Recent discoveries have confirmed that circumbinary planets exist and can orbit in or near their stars' habitable zones. These systems add more candidates to our search and demonstrate that planetary systems can form and remain stable in configurations more complex than our own solar system's simple single-star arrangement. All these extensions and complications remind us that habitable is a more flexible concept than it first appears. Life might find ways to exist in environments we haven't imagined. It might use different solvents than water, different energy sources than starlight, different chemical building blocks than carbon. We search for what we know, for conditions like those on Earth, because that's our only example of life, and because those conditions are what we know how to look for. But as we search, we should remain humble. The universe is more creative than we are, and life, if it exists beyond Earth, might surprise us. Let's take stock of what we've learned. A habitable planet requires the right orbital distance from its star to receive energy that allows liquid water to exist, an atmosphere thick enough to provide greenhouse warming and pressure, but not so thick it creates runaway heating, a magnetic field strong enough to shield that atmosphere from being stripped away by stellar wind, sufficient planetary mass to generate strong gravity to hold the atmosphere and to maintain geological activity, active geology to regulate atmospheric composition through volcanism and tectonic recycling, a star of appropriate type, massive enough to have a reasonably wide habitable zone, but not so massive it burns out before life can evolve, a star calm enough not to sterilize nearby planets with excessive flares and radiation, a planetary orbit that remains in the continuously habitable zone for billions of years as the star brightens, and probably other factors we haven't even identified yet, perhaps a large moon to stabilize the planet's axial tilt, preventing extreme climate swings, perhaps a Jupiter-like planet in the outer system to deflect comets and asteroids, reducing catastrophic impacts, perhaps a particular atmospheric composition that we haven't thought of yet. Each requirement represents a dial that must be set within a narrow range, too far in any direction, and habitability fails. The orbital distance must be within about 20% of the optimal value. The atmospheric thickness must be within perhaps an order of magnitude of Earth's. The planetary mass must be large enough to hold an atmosphere, but not so large it becomes a mini Neptune with a hydrogen envelope. The star's mass must fall within a relatively narrow range, probably between 0, 6, and 1.4 solar masses for best results. The planet's geological activity must persist for billions of years. When you multiply all these probabilities together, when you account for all the ways things can go wrong, you arrive at a sobering conclusion. Earth-like habitable planets might be relatively rare. Recent statistical work analyzing the known exoplanet population suggests odds of roughly 1,600 to 1 against red dwarfs hosting advanced civilizations like ours. Since red dwarfs make up 75 to 85% of all stars, this removes most of the galaxy's stellar population from contention. That leaves F, G, and K-type stars, which together constitute perhaps 20% of stars. If only some fraction of those have planets at the right distance with the right properties, we might be looking at tens or hundreds of millions of potentially habitable worlds in the Milky Way, not billions or trillions. Tens of millions still sounds like a lot, and it is. But spread across a galaxy 100,000 light-years in diameter, tens of millions of habitable worlds means the nearest might be dozens or hundreds of light-years away. We could search for decades or centuries before finding a truly Earth-like planet with clear biosignatures. This is one resolution to the Fermi paradox. The troubling question of why we haven't detected any signs of extraterrestrial intelligence, despite the galaxy being old enough that even very slow technological civilizations should have spread everywhere by now. If habitable planets are rare, and if the emergence of intelligent life is rarer still, then perhaps we're alone in the galaxy. Not because life is impossible, but simply because the universe is more selective than we hoped. But there's an equally valid opposite perspective. The galaxy contains at least 200 billion stars, perhaps as many as 400 billion. Even if only 0.1% of stars host habitable planets, that's 200 to 400 million habitable worlds. Even if only 1% of habitable planets develop complex life, that's 2 to 4 million worlds with complex ecosystems. Even if only 1% of those develop intelligent technological civilizations, we're talking about 20,000 to 40,000 civilizations in our galaxy alone. We've only just begun searching. We've characterized perhaps a few thousand exoplanets out of trillions that exist. We've observed a tiny fraction of the stars with enough sensitivity to detect biosignatures. We've been listening for radio signals from extraterrestrial civilizations for only about 60 years, a geological instant. Our telescopes and methods improve every year. The James Webb Space Telescope is just beginning its mission. The next generation of extremely large telescopes on the ground is under construction. The Habitable Worlds Observatory is being designed. Perhaps we simply haven't looked long enough or hard enough yet. Perhaps life is common, and we'll find it in the next decade or two. Perhaps the galaxy is full of planets with microbial ecosystems, even if technological civilizations are rare. Perhaps we're on the verge of the greatest discovery in human history. The confirmation that we are not alone. Or perhaps we are alone. Perhaps Earth's long list of fortunate circumstances is so improbable that we represent the only instance of complex life in our galaxy, possibly in our entire observable universe. Perhaps we are extraordinarily lucky, the beneficiaries of cosmic coincidences so unlikely they might not be repeated anywhere else. We don't know. We can't know, not yet, but the search itself ennobles us. The question itself reveals something profound about our nature as conscious beings. We look outward and wonder. We seek to understand our place in the cosmos. We refuse to accept isolation without investigation. And in searching for other habitable worlds, we've come to understand our own world more deeply. We've learned how delicate Earth's habitability is, how many things had to go right for us to be here. We've learned that the ocean beneath our feet, the air we breathe, the magnetic field shielding us from space, the geology churning beneath the crust, all of these represent gifts from the particular configuration of matter and energy that formed our solar system 4.6 billion years ago. Earth sits at 1 AU from a G-type star. It has a mass of 5.97 times 10, 24 kilograms. It has an atmosphere with 21% oxygen and enough CO2 to provide moderate greenhouse warming. It has a magnetic field generated by a molten iron core. It has plate tectonics that regulate carbon dioxide. It has a large moon that stabilizes its axial tilt. It has liquid water covering 71% of its surface. It has maintained all of these properties within habitable ranges for at least 3.5 billion years, allowing life not just to emerge but to diversify into millions of species, eventually producing creatures capable of contemplating the stars and asking whether anyone else is out there. We are, whether common or rare, extraordinarily fortunate. The night sky above you contains roughly 6,000 stars, visible to the naked eye from any single location. Each of those stars might have planets. Many of them certainly do. And around some of those stars, at just the right distance, with just the right conditions, there might be worlds where water flows, where atmospheres retain heat, where life has taken hold. But we don't know which ones. We can't see those worlds directly, not yet. We can infer their existence from subtle wobbles in starlight, from tiny periodic dimming, from painstaking analysis of spectroscopic data. We can build models and run simulations. We can calculate probabilities and refine our search strategies. But we cannot, from here, simply look up and point to a star and say, "There, that one has a living world." Not yet. This uncertainty is both frustrating and wonderful. Frustrating because the answers we seek might take decades or centuries more searching. Wonderful because it means the question remains open. The possibility remains alive. We live in an age where we might be the generation that discovers we are not alone, or we might be the generation that begins to suspect we are. The Goldilocks planets, those worlds where conditions are just right for life, exist somewhere out there. The statistics demand it. Even if habitable worlds are rare, the galaxy is vast enough to contain them. Even if the requirements are stringent, chance and chemistry have had billions of years to produce habitable outcomes. Perhaps there's a world orbiting Alpha Centauri A or B, our nearest sun-like stellar neighbors at 4 light-years distance, where oceans lap against rocky shores and clouds drift through alien skies. Perhaps one of the TRAPPIST-1 planets, 40 light-years away, hosts simple organisms in its seas, life that never evolved past the microbial stage, but life nonetheless. Perhaps somewhere around a K-type orange dwarf, 100 light-years distant in the direction of Cygnus or Lyra, a planet has developed complex ecosystems, forests and grasslands and oceans teeming with strange forms we would recognize as living, even if we couldn't imagine their specific shapes. Or perhaps not. Perhaps Earth is singular, the only inhabited world in this vast galaxy. Perhaps the requirements are so stringent, the dice rolls so unlucky for almost everyone else, that we represent a statistical outlier so extreme we might as well be alone. We cannot know which of these possibilities is true without continuing to search. And so we build better telescopes, we refine our models, we catalog stars and characterize planets. We design missions to send spacecraft to Europa and Enceladus to probe their subsurface oceans. We plan the Habitable Worlds Observatory to directly image dozens of potentially Earth-like planets and analyze their atmospheres for biosignatures. We continue the work, generation after generation, asking the ancient question in increasingly sophisticated ways. Are we alone? This question has driven human curiosity for thousands of years. Every culture has wondered about the stars, speculated about other worlds, told stories about life beyond our own. Only in the last few decades have we developed the tools to actually answer the question through observation rather than imagination. We stand at a unique moment in human history. The transition from speculation to science, from wondering to knowing. And regardless of what we find, the search itself matters. It teaches us about planets and stars, about atmospheres and geology, about the intricate web of conditions that allows life to exist. It shows us how precious our own world is, how many things had to go right for us to be here. It gives us perspective on our place in the universe, humbles us before the cosmos's vastness, while simultaneously showing us the remarkable nature of consciousness that can contemplate that vastness. If we find life elsewhere, we learn we are not unique. We learn that the universe is full of living things, that the chemistry and physics that created us have created others. We might learn about radically different forms of life, different biochemistries, different evolutionary paths. We might learn that intelligence is common or rare, that technological civilizations are robust or fragile. We might learn we are members of a vast community scattered across the stars. If we don't find life, if we search for centuries and find only dead worlds and sterile atmospheres, we learn something equally profound. We learn that consciousness is precious beyond measure, that we carry the universe's flame of awareness through a mostly dark cosmos. We learn that we bear a responsibility not just to our own species, but to the very principle of life itself, because if we fail, there might be no one else to carry it forward. Either way, we learn our significance, either as rare or as common, either as alone or as companioned. The answer changes our self-understanding fundamentally. But for now, tonight, the answer remains hidden. The question hangs in the dark between the stars, and perhaps that's appropriate. Perhaps we need this time of uncertainty, this space where wonder can live alongside science, where we can contemplate both possibilities and remain open to either outcome. As you drift towards sleep, as your thoughts become less linear and your consciousness begins its nightly journey into dreams, carry with you this image: a universe full of stars, each one a possibility, each one holding the potential for worlds where conditions might be just right. Somewhere among those countless points of light, perhaps water catches starlight on an alien shore. Perhaps clouds drift through an atmosphere not so different from our own. Perhaps life exists, has existed, will exist, in places we haven't even imagined yet. We are here, conscious and curious, asking questions about worlds we cannot yet reach. That alone is remarkable. That alone justifies the search. And if some of you have found comfort in this journey tonight, if these ideas and images have helped quiet your mind and ease you toward rest, then perhaps you might consider liking this video or subscribing to see more of these explorations. Your support helps me continue creating these long-form contemplations of cosmic questions, these bridges between science and the search for meaning, these attempts to understand our place among the stars. But whether you do or not, I'm grateful you've spent this time with me, wondering about Goldilocks planets and habitable zones, thinking about what it means for conditions to be just right, considering the delicate balance that allows life to flourish. Rest well. The stars will still be there tomorrow, holding their secrets, waiting for us to uncover them. And somewhere in the dark between the worlds, perhaps, an answer waits. Good night.